All right, so here we have a simple circuit wired in parallel. And for this one, we follow the same general, actually for all of these, we're just gonna follow the same general hints that I like to follow that I, again, have found useful. And really quick, let me just change the color of my little pen here because I don't like the blue, I don't like the red. So, number one, have the Ohm's law equations available. So again, if I don't have them written on this, I'm just gonna write them on my thing right now. V equals I times R. I is equal to V over R, and R is equal to V over I. And then of course, power is equal to IV. Power is equal to current times voltage in our case. There's other ways to find power and they will work just as well, but that's the simplest one. So what do we do here? Well, same thing as last time. Look for any givens first, and there are 3 givens, so I'm going to fill those out. We got one, just like last time, we got 10 volts for our total, 10 volts coming out of the battery, 10 volts across the battery. So the battery is raising the voltage to 10 volts. It's raising the energy level 10 volts. Then we have 2 resistors, the 15 ohm resistor and a 30 ohm resistor. Okay, and those are the 3 givens. So we could pretty much be, not even pretty much, we could be done with givens. We don't have any more. So now I look for easies, and right now we don't know any easies. In other words, this is a parallel circuit, so we don't know the voltage across one. Well, actually we do. We do know the voltage across one. So we know that, I was wrong. Easies, we got 10 volts up here. So in other words, up here we could say is 10 volts. And that means everywhere is 10 volts no matter how you go. So in other words, we are at the top of this diagram at 10 volts of energy. Okay, 10 volts of electric potential energy. And at each resistor, it's going to drop. How much? 10 volts. At each branch, each resistor in this case, it's going to drop 10 volts. So we know that this is 10 volts. And this is 10 volts. In other words, the easies, quote unquote easies in this case, is that the voltage drop at each branch is going to be the same. All right, so in this case, we know it's going to be dropping 10 volts. Okay, so there's a couple ways we could go about from here. One way we could do it is just kind of thinking ahead, is again, I'm going to leave power for last. Okay, I'm going to figure out every other box first. And there's a couple ways we could figure out current here and current here, and then add the current up because the current comes together and we get our total current here. Then we can figure out the total resistance. And I like that. But another way to do it is to calculate the total resistance first, figure out the current, and then figure out the current. And then either way, it will work for you. In fact, you could probably try both ways. But because I want some practice calculating the total current in a, total resistance in a parallel circuit, I'm going to do it this way. So I'm going to take the inverse of 15 ohms plus the inverse of 30 ohms. And that, now remember in your calculator, we talked about this in another video. Basically, I'm going to put 15 to the -1 plus 30 to the -1, the inverse, in other words, in my calculator, just like that. So 15 inverse plus 30 inverse. And that gives me an answer of 0.1. So either way, it's going to give you 0.1. And then you have to take the inverse of the answer. And so my total, inverse of that is going to be 10. So in other words, we take now 1 over that, and that should give me 10. So my total resistance is 10 ohms. Now, if you don't quite understand why is the total resistance less than the other resistors, that's how a parallel circuit works. You have more branches, you have more choices for the electrons to flow through. And in an analogy with traffic, for example, or the hallways in the school, if you have more hallways for people to walk down or more roads for the cars to drive through, it doesn't matter the resistance for each choice. The more choices there are, the less overall resistance you're going to get. In fact, this is one of the clues that you're doing it correctly, is the total resistance should be less than any of the individual resistors or branches, or I should say any of the individual branches, any total branches. And when we get to more complicated circuits, you'll see what I mean. Okay, point is, we now have our total resistance, and we can now calculate, and we can just go through boom, 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 calculate the current at each resistor or at the total. So current is, this is why I write it all down, V divided by R. So V divided by R, so 10 divided by 10, that's pretty easy, 1 amp. So now we're going to kind of like expect that 1 amp is going to split up somehow. And because the resistors are not the same, it's going to split up unevenly. But the total should be 1, should add up to 1 because, well, it splits up from 1 and then it's going to rejoin and become 1. This is the flow of electrons. So current is V divided by R. So I'm going to take my voltage, 10 volts divided by 15 ohms. And so for the first resistor, the 15 ohm resistor, I'm going to get 0.0, whoops, that's a 0.67 amps. It's actually like 6666666 infinity to, 2/3, in other words, of a current, of an amp. And then we have 10 divided by 30 for our last one. And that's going to be, of course, 0.3333333. Infinity, of course, 3 amps. Does that add up to 1? It does. So we're good. All right. So power then is just I times V, current times voltage. Well, that's easy for here, 10 watts of power. Now, these resistors should add up to 10. So let's see how we do. Well, yeah. So 0.67 is going to add times 10 is going to be 6.7 watts. 0.33 times 10 is going to be 3.3 watts. That adds up to 10. So we are good. That's it. Just follow the same steps as usual and you should be good with this.